So, and actually I'm going to clear this so we can summarize a little bit better. So, the big thing to get from our last chapter is you take a ring with an electrophile, the pi bond attacks, you end up with the electrophile attached, positive charge, you end up drawing resonance. Okay. You should be drawing at least 3 resonance. I'm not going to draw the middle one. Fine, I'll draw it. Just because everybody's complaining so much. Jeez. Must be a good artist or something. Draw a little happy tree. Sorry. Abstract. When we remove the hydrogen, our last step, and we have our full substitution. Right? So when we're looking at this mechanism, the big things that come out of it is you need to know these resonance structures. You get tested on those. Okay? You get tested on being able to draw those. Resonance is huge. It drives everything we've done this semester. You need to be drawing those resonance structures. Okay? Yes?
It goes back to the substituent, right? It's like if it's electron donating.
So I haven't even gotten there yet. This is just review from last time. Okay? At this point, we're starting with benzene. All hydrogens are equally available, so there is no difference here. So we have to look at those resonance structures to be able to just say it works. Okay? What happens in the next unit is we go through, is we now change the structure and we put a substituent on. So if we look in the upper left-hand corner, notice that now those hydrogens are all different because they have a different spacing to atom X. Okay? Because they're different, we're going to have some different chemistry associated with those. We have to be able to predict which of those hydrogens is most likely. Okay? And there are 2 approaches to that. One is just starting straight out of the gate and showing resonance structures. Where does the negative charge build? That is officially the wrong way to do this. It works beautifully, but it's wrong. Okay? Officially, what you're supposed to do is say, well, I think it's going to go to the ortho position, so I'm going to put a substituent there. And now I'm going to show all the resonance structures. Well, I don't know if that's the correct answer, so I'm also going to show it going to the meta position and draw all of those resonance structures and then compare. Okay, yes, that's a lot of extra effort and work, but that's the official correct way to do it. Okay? What this system does, though, is it sets it up so you can see those charges and see where those things build. So I would highly encourage this, but you have to be applying this. As soon as you see a benzene ring with a substituted piece, you have to be doing this. You have to be thinking this. If you're not, you're already in the hole. Okay? And you can't expect to get out of it. And that's okay. Accept it as a loss, move on, go back to the stuff that you don't expect to lose. Does that make sense? Yes?
Would it be enough just to figure out, based on the substituent, if on what carbon we're going to have the electrons?
So how do we know which carbon to have the electrons? Well, one is you draw all the resonance structures.
Yeah,
the
like that.
Other option, which is where I think you're potentially suggesting, is that you look at that atom X and you decide, does it have more electrons than hydrogen? If it does, then it's an activator and I substitute para and ortho. That's fine. You've memorized that rule. If you want to memorize that rule, by all means, there's a reason I put this unit at the very end of the semester. It's because this stuff applies to very few locations. Okay? Most of you are going into some kind of pre-health-ish profession. Aromatic structures are useless. That's a bit of an overstatement, but not very helpful. Okay? So I don't want you to waste time processing this. Instead, what I want you to do is just pick up the bare bones of it, just apply it real quickly if you see questions like it, and then move on. Okay? So this could be something that you memorize. You draw out a benzene ring with an atom X. Atom X has more electrons than hydrogen, activator, para, ortho, and you write that down when you get the test. Okay? You don't write it on the test. You're not allowed to write on the test, but I'll give you a crap ton of scratch paper, and as soon as I tell you to go, you can write whatever you want on that scratch paper. That is fine to go ahead and write this information. But you have to be able to come back and reference and find it. Okay? This goes for the homework too. You should be referencing this. I don't expect you to have it memorized yet. Okay? Arguably, I don't expect you to have it memorized at all because it's not that important. Okay? What I do expect you to be able to do is reference it. Go back, find the information, and use it. Okay? That's what you need to be doing. If you go back and review something and you'll be like, damn, I had to have that memorized. There's no way I was going to be able to derive that. That's cool. Write that down. You now know that when you come to the exam Wednesday, is what we decided for most of you, or Monday?
No,
Right?
Tuesday.
6 a.m.
I'll hold you to it. That you have to be ready to write that information down, okay? And you should be just writing it down. Don't worry about what's on the test right away. Write that stuff down. Spend the 5 minutes and get that information purged so that you can use it later. Okay? So the other big lesson out of it is we keep looking at atom X having more electrons. Atom X can have less electrons. That becomes a little bit harder to see. Okay? The example given here becomes a little bit more apparent because atom X is positively charged. That one becomes kind of obvious. Okay, where that becomes a little bit less obvious, say if it's a nitrogen. You go, well, atom X is a nitrogen, then it has more electrons. Not if it's positive. The only way you become positive is because you don't have electrons. To become positively charged, you're actually missing electrons. Okay? So when we're comparing back to hydrogen, we have to consider that charge. Okay? The classic example is, say, nitro. Okay? For those of you that were in the lab, we had a ranking of substituents, and it's looking at those charges. How strong is that positive charge? The more formally positive it is, the more deactivating it is. Okay? The more willing there are, or the more ability that there are electrons to donate, the more activating it is. So we're just applying those rules and trying to match them up as best we can. Kind of make sense? Okay. After that, we actually get into content, and that's where it becomes more difficult because there's now kind of, I wouldn't call them exceptions, but additional rules that we have to watch out for. Okay? When we talked about the Friedel-Crafts with the aluminum chloride, okay, the alkylation is a relatively mild electrophile. Okay? That's because it's not easy to form carbocations. So the Lewis acid catalyst helps kind of initiate that and get that going, but that carbocation is not particularly strong. We form very small amounts of it. So the only reason it can react with the ring is because the ring is ready to react with it right away. But that means the ring has to be a strong nucleophile. Well, benzene isn't a strong nucleophile. That's why benzene rings don't react. Okay? It has to be activated. That's why we have to have a methyl group, an oxygen, or a nitrogen attached to the ring to help activate it, to allow for the Friedel-Crafts alkylation to occur. For the acylation, the one down at the bottom, we don't have to worry as much about. The reason why is that I form a much more stable carbocation. That carbocation is stabilized through resonance. Okay? I didn't get to make this joke before, so we'll make it now. This is one of my favorite ions. Anybody know why? It's kind of a silly reason. It's the acylium ion. Yeah, that's the acylium ion. Sorry, I just had to share that. Okay, I can be terrible. It's fine. It's the end of the semester. You expect nothing less. Okay, because that is resonance stabilized, that can exist for long enough that I don't have to have a superactivated ring. Okay, that reaction can happen more quickly and easily. Okay. As we kind of alluded to, though, or also, let's see, do I have this on a slide? I don't. This is another part that we'll worry about. So we'll look at this and hopefully it comes back. The amine becomes problematic. Okay, if we look at aniline. Yes, that nitrogen has extra electrons. Yes, that nitrogen can activate the ring. But what can that nitrogen also act as? A base. Okay? If it reacts as a base, we're saying it picks up a hydrogen. So ignore what's shown there for the moment. Go away. Go away. come back again. Like that song, right? We could have it react with a hydrogen. What's the result if it reacts with that hydrogen? H3. That nitrogen is now positively charged. What is the issue with that now? Now that group's a deactivator. It started as an activator, now it's a deactivator. Your substitution pattern happens in the wrong place. Crap. Okay? That makes things difficult. Okay? So we have to watch out for that nitrogen chemistry. It's a pain in the butt. Sometimes it shows up when it rears its head and it's a pain, sometimes it doesn't. Okay? And a lot of times it's really just coming out of the question. Look at your answer choices and critically evaluate, where do I think this is going? And if it comes down to a 50-50, 50-50, pull your gut shot, do what you got to do. Okay? Why is it coming up again in the Friedel-Crafts alkylation? Okay, well, here we're saying it acted as a Bronsted-Lowry base because it did what? Accepted a hydrogen. How did it accept a hydrogen?
Shared electrons.
It shared electrons. Is there another definition about something sharing electrons? Lewis bases. What's the problem with the Friedel-Crafts catalyst? That's a Lewis acid. So what happens when we add a Lewis base to a Lewis acid? Oh, those two things react with each other. Okay? Much quicker than the chloride from our alkyl substitution. Why would the nitrogen react with the aluminum chloride faster than the chloride? Because remember, in theory, what else is floating around in solution would be our RCl, right? And the whole point was that the chloride shares with the aluminum trichloride to give us the R positive. Why does our now purple reaction happen faster than the red?
Chloride is more stable with the negative charge.
This one gets a little bit weird. The nitrogen is more willing to share those electrons than the chlorine. Okay? Don't ask too many questions after that. Let's just kind of accept the nitrogen is more willing to share those electrons. If nitrogen is more willing to share those electrons, then it's going to react with the aluminum chloride. If it reacts with the aluminum chloride, it does a couple things. First off, what does it do to our aromatic ring? It deactivates it, it slows the reaction. Number two, the aluminum chloride is now on the nitrogen. Is there any aluminum chloride to react with the alkyl halide? No. So is there a catalyst to make the electrophile? No. So not only did we destroy the nucleophile, but we now don't have a way of making a good electrophile. The whole thing is shot. Okay? So having amines in Friedel-Crafts reactions does not work well. Okay? So in general, they don't work. So if you can avoid them, do so. Okay? And that's kind of a complication of those reactions. Okay? Here's the other issue. So let's take a look at just our alkylation. So this case, it's a Friedel-Crafts alkylation because we just have an RCl. So there's no carbonyl, RCl. We've got our Lewis acid. I'm not using nitrogen. The oxygen isn't as willing to share the electrons because it's more electronegative. Okay? So we might expect this to go through our standard EAS reaction, all the aromatic or all the resonance structures, all that fun stuff, and we would generate a product. Where would we expect the substitution to happen? So I'll give you 5 seconds, and then you actually have to draw the whole mechanism. Okay, so somebody decided to jump in there. Okay. The para and ortho positions should be reacting. Why should the para and ortho react? Atom X has more electrons than hydrogen. That means it's an activator, para-ortho directing. We would expect the para over the ortho because there's less substituents or there's less sterics blocking the para position. The ortho is blocked a little bit by the O-methyl. Okay? So we would expect the R group down here, there's our CH3. Okay? As we've done in the past, though really we haven't drawn a whole lot of attention to it, we just kind of only brought attention to it when it mattered, we need to look at our product and decide, should we stop? What is reactive about our product? The pi bonds. You mean the same thing that was reactive about our starting material? Yes. Okay. So we're talking about our pi bonds being reactive. When should we stop this reaction?
When they are less active than.
When our product pi bonds are less reactive than our starting pi bonds. Does that make sense? Right? And we've done that in the past. If our product was more reactive than our reactant, well, we kept doing the reaction. So now we've got to evaluate the pi bonds in our product. Are those pi bonds more negative or less negative than the starting? Why are they more negative? What is the difference between those structures?
Isn't the methyl group also donating electrons?
What is it different than? Yes. Hydrogen. We are comparing that hydrogen to that methyl. Does the methyl have more electrons than that hydrogen? Yes, which means it can donate electrons to the ring, making the ring more active, which means do another substitution. Okay. We want to substitute where? This is a tricky one because we haven't talked about this yet.
Both positions are valid.
The ortho position. Ortho to what? Okay, so we'll make the methyl green. We'll keep the O-methyl purple. Where is the ortho position to the oxygen? Is it up here? Is it down here? Am I getting hotter or colder? I'm getting colder. Okay, so you tell me. Hot or cold? Warmer? Where is it? Okay, there we go. So there's our ortho position. Okay. We also have another ortho over there, right? Where's the ortho position to the methyl group? Same spot? Ooh, no, it's the other spot. All four positions are now active. Where do I expect the substitution? Why? Okay.
Because the carbon was more recently put on.
Okay, so that's not a bad idea. The green one, the methyl group, was more recently put on. So when we run our reaction, we decide we react to the things that were more recently added. There wasn't something else that we used to decide. What do we use to decide what reacts? Electrons. Which electrons? Why pi bonds typically over sigma bonds? Higher energy. I'm looking for the most reactive, right? That's the one that dictates my reactions. Are the pi bonds that are ortho to the methyl group more active than the ones to the oxygen? So some people are saying no. Why?
Because oxygen has more electrons.
Oxygen has more electrons. It's not just a question of it having electrons, but it actually has lone pair electrons that it can share via resonance. The methyl group does have more electrons than hydrogen, but does it have electrons that it can share via resonance? No. What does that mean happens? The ortho positions to the oxygen are more active than the ortho positions to the methyl, and I would expect substitution to happen up at the top. And yes, I would have to go through and draw out all my resonance structures, and we would end up with this fun and dandy looking structure. Now what do we have to do? Why do we react it again?
Because the methyl that you just added is more active than the hydrogen.
The methyl that I just put on was more active than the hydrogen that was formerly there. That means the structure is more active than it was to begin with, and now what happens? You do it again. Okay. Where do we do our substitution? Ortho to the oxygen again. And we would end up with this structure. This structure is now still even more active than the starting material, but the oxygen's the one that dictates the chemistry. Okay, because it was the most directing. What does that mean happens now? It stops because there's no more places it can substitute. It can only substitute based off of that oxygen. So now the reaction stops. I've ended the reactivity, not because it's less active, but I literally can't do substitution at those positions. There's tons of electrons there, but it can't do a substitution because there's nothing to substitute for. Okay? So this becomes a problem with the Friedel-Crafts alkylation. We're putting on a group that activates the ring, which only means it's going to react more. So we would do Friedel-Crafts alkylation only if we wanted to keep doing Friedel-Crafts alkylation. If we only want to do a single substitution, Friedel-Crafts alkylation is not the way to go about it. So what could we do to fix that? Let's see, did I do it? I just drew pretty pictures. That's where we could do our acylation. Yeah, of course I didn't draw it. What would be our new method? This would be a bit obnoxious, unfortunately. So let's switch this up to CH2, CH3. If I wanted to put on 2 carbons, whoops, I would go through the acylium. This is now going to do a single substitution at the para position. Is that even showing up on the screen? Barely. Why does the reaction stop after that one substitution?
Two areas that are, or 2 oxygen areas that can't contribute.
No, officially we only have 1 oxygen that contributes to the ring. The other one's a carbon. Why does the reaction stop after only 1 substitution? That blue carbon deactivated the ring. Okay? So now my product is less active than the starting material. It stalls there. Okay? That's why the acylation tends to be more common than the alkylation, because the acylation will do a single substitution. It's selective. The alkylation, not so nice. Okay? But what if I just want an alkyl group there? Do I have chemistry to remove that carbonyl? Yes. That's now stringing in extra chemistry. I don't know why this pen seems so fine, you know. Is that legible? It seems really weird. What did I do? That's a little better. Someone help me out with the reagents. I'm not good with my, well, here I can just cheat. H2 and platinum, that will reduce away the carbonyl. I'll now be left with my alkyl group. And I've done my proper substitution. If I only wanted one methyl, though, how could I do that? That gets significantly harder.
Can you oxidize the benzylic carbon and then...
That's the only way I've got tumbling through my head is, yeah. You would use, because I don't know that you can actually use the formal chloride. I'm not sure you can even do that. But if we use the same reagent, we would oxidize first. So if I only wanted the simple methyl, I would go through and use something like permanganate. And potassium, by the way, does not have an N as a second symbol. This would take me to the carboxylic acid. I've now lost that carbon, but I don't want the carboxylic acid. I wanted the carbon, so what can I do? Now I could reduce. Right? Gave me a mildly weird face on that one. Benzylic position, remember we can fully oxidize that down to a carboxylic acid using permanganate. It's not as simple as just KMNO4. You could also use chromic acid, H2CrO4, I think. Okay, so any one of those chromic acids or permanganates. Those will take you to the carboxylic acid. Make sense? Okay. The one that I whipped through really quickly at the end of last lecture was our weird aromatic halogens. Halogens are kind of bizarre because they have more electrons than hydrogen, which would suggest they're activators, but they're also electron withdrawing because they don't want to donate their electrons, making them deactivators. Okay? So when we looked at that nice clean definition of activators, deactivators, the halogens fall dead in the middle, which mess with the entire system. Okay? They fall so far in the middle that they end up applying, whoops, both definitions. Okay? They end up being deactivators, and they will slow further substitution. Okay? But they will direct substitution to the para and ortho positions. Okay? And that's because the electrons align in the pseudo-pi system that stabilizes the para and ortho, having more electrons in the meta position. Okay? Not a happy explanation, but that's the way it works. Okay? So when it comes to EAS, you've got three things to memorize. What an activator is, what a deactivator is, and then halogens being that weird crossover in between. Make sense? Okay. So what about multiple substituents? So let's take a look at that first one. Okay. Based off the reagents, what should we be seeing? What is our electrophile? Bromine. Okay. We look at the other reactant. The only thing we have a source of electrons is our pi bonds. So we're going to be pulling electrons out of the pi bond to do a substitution for a hydrogen. So the question then becomes, which hydrogen? Okay. Well, just like we did with the Friedel-Crafts alkylation problem on directing, we want to direct based off of the strongest activator. Which of those is the strongest activator? Doesn't nitrogen have more electrons than hydrogen? How do you know it's positive charge? Touche. Because you know what nitro is. If you got it memorized, I'm cool with that. You need to remember that that nitrogen has that positive charge. That is a deactivator. It's an electron withdrawer. So the methyl group is going to dictate the chemistry. Because the methyl group dictates, we're going to expect to see substitution where? Para and ortho. So we now have one of those positions eliminated. We do not expect to see substitution there. What about the other positions? Which of those do you think is most likely and why?
The left ortho.
So you're saying what I just now labeled as position 1? Somebody want to agree or disagree?
I agree.
Okay. Somebody else now gets to explain. See what I did there? I don't quite accept that.
2 and 3 are more sterically.
You're saying that this nitro group with those groups of electrons are now blocking those positions? I think that seems reasonable. Yeah. That nitro is probably going to block out those positions, and we would expect that the one ortho position is going to be the most likely to do the substitution. I agree. Okay. What about the bottom one? So the first thing we should be doing is, because we memorized all of our reagents, I know you haven't yet, but that's okay. Nitric acid and sulfuric acid get us what electrophile? The nitronium ion, with our nitrogen being the positive. Where's our substitution occur? Ortho to the oxygen. Why to the oxygen? The oxygen is more activating than the methyl group, so I would expect the substitution to happen there. Which one of those positions is more activated than the other? You're right. It doesn't matter. I was hoping for a long pause, and I would ask for left or right, and then I would say you were wrong by drawing the other one. But you're absolutely right. There is no difference between those two. You end up with the exact same product. It might look different, and remember, they can draw structures flipped over, so you have to watch out for that. Okay? Make sense?
So then it wouldn't react again with another nitro group?
Why would it not put another nitro group on?
Put on something.
Nitro is a deactivator. Okay? So as an interesting kind of observation, let's clear all that away. You heard of TNT? Did Brian draw that one out for you? What do you think? Easy to make or hard to make? Why would that be hard to make? Nitros are all deactivating. To get 3 deactivators onto the same ring, you've got a lot of deactivation to do. It's not an easy reaction to run. Okay? You're probably going to have to use heat and lots of concentrated sulfuric and nitric acid. What's problematic with that? Come on. TNT
Probably blow up.
is an explosive. So yes, we've put a very high strain on that structure. That's one of the reasons why it's dying to bust apart. We give it the right spark or initiator, the whole structure flies apart to stabilize and not be so messed up. Okay? That is one of the reasons why it's explosive. Okay? So it's not an easy stuff or easy material to produce because it's a highly deactivated structure. Okay? So, lesson, activator trumps deactivator, stronger activator trumps weaker, which is really the same thing. Activator trumps deactivator. Okay? And stronger activator trumps weaker is really the same thing as the first one. We're just now changing the wording slightly. Yes?
So on the second one, when we added a nitro group, we still have the activators. Why did we stop there?
The nitro is that strong of a deactivator.
How about the first one? So the first one we had a...
The nitro is that strong of a deactivator, and you added bromine, which is a deactivator.
Yeah, but why the first one reacted even though it had the nitro?
Oh, I see what you're saying. Yeah. Because of the catalyst. The other part of it that's going to be kind of backhanded because they drew it, because we asked the question. You should be doing single substitutions. If we're showing it to you, you should be doing single substitutions. The exception being the Lewis acid, the Friedel-Crafts alkylation with amines. That's the one you have to watch out for. But yeah, fair question. I didn't see that right away. How about these? First one, where do you expect substitution to happen? One, two, three, four. Why is this more challenging? They're all carbons. They're all the same level of activity. So 1, 2, 3, 4. 2 or 3. Do I get a second?
I was just against, don't trust me.
1 or 4.
1 or 4. Ooh, wow. Okay, full on switch. Okay, so we got a challenge. So we got a 2, 3, a 1, 4 with a challenge between those two. Does someone want a second to one of those? I got a second for 2, 3, which then means somebody else gets to explain. Would it help if we drew what the product would look like? Okay, so let's go ahead and draw the product out. Okay, fascinating that you're saying that it's helpful if we draw structures. Wonder if someone has talked about doing that, like the entire semester. Someone talking about themselves and say the third person. No one would do that, though. That would just be silly. So, purple's the equivalent of 1, 4. Blue is our equivalent of 2, 3. What do you guys think? Why 2, 3? Sterics. 4, the large group is near the largest group. Okay, in the 2, 3, our large group is near the smallest group. Okay, so the difference between those substituents is really nothing as far as their activating or deactivating ability, in this case activating, but they do have a difference in sterics. Okay, so when we go through and evaluate things, we evaluate first the electronics, like charge, and then we'd start to evaluate subcategories like, I don't know, size, then maybe electronegativity, then resonance, then induction. Oh, you mean we're using the same things that we've used? Yes, yes, we are. Okay, makes sense?
So it doesn't matter that we have a tertiary versus a primary carbon. It doesn't have any electrons.
Yeah, there's not enough of a difference in electron density there to do anything. The bottom one? 1, 2, 3, 4. 2.
Or 1.
2.
Oh, everybody's saying 2 now. Okay, why?
Because it's para for one of them and it's ortho for the other one.
This one would be para, ortho, ortho. This one would be para, ortho, ortho.
It's also closer to the smaller one.
Okay, so you should be saying that 4 and 2 are the most likely, okay, because they're both having a para characteristic come out of it. 2 has putting that now larger group near the smaller of our 2 current substituents, so the 2 position is probably the most likely to come out of this. Okay, that's where we'd expect our higher yields. Okay, so if we go through and act, let's see, did I put the yields in? That would have been nice. Oh well. So I didn't put the yields in, but they do heavily favor the least sterically hindered substituent. Heavily, I think you're probably 60-40 maybe. Maybe as much as 70-30. Okay, kind of makes sense? Okay. Directing effects and reversibility. How do we make that product? What changed?
Substitute of bromine.
Bromine for a hydrogen, the reagent to do that. Br2, FeBr3. Sweet, awesome. Does that work? Probably not. Too simple. What went wrong? Sterics would suggest the ortho position is not likely to happen. What did the electronics say? Well, I mean, it's sterics all the way, actually. So steric says para should happen before ortho. And then even further, that's a tert-butyl group that has massive sterics. We should expect a large favoring for the para. And instead, we're getting the ortho. So that likely means this is not a good reaction.
You need to add something to the pair first and then take it off.
We need to put something on at the para position first to block it, then do the bromination, then undo. Okay, so block, and then unblock. What do you got? If it helps, I can come up with a couple answers, I think, off the top of my head. Maybe. And by a couple answers, I mean, I know generally what the reagents would be, but I'm not positive. There was one that we said was outright reversible. What was it? Sulfuric acid. Okay, which the textbook and the homework has been being nice and writing SO3 above it. Okay, I don't think anybody's going to be ever that nice, and they'll just say sulfuric acid. Okay, what'll end up happening then is you've done your substitution. I don't know why I decided to draw out the Lewis structure. Okay, which would then block. How would you unblock it? Sulfuric acid again, and I believe you have to add a little bit of water this time, okay, to help unblock. And then that would remove it. So that works. What's the other option? Yep, we totally don't remember the reagents. But I know you can do it. Ooh, I think I got it. Unblock H3PO4, maybe PO3. Here's where we would then have to do the bromination. Be super important to do it there. What were all the reagents for this one? Sodium nitrite, diacid. I'm just going to say H+. That way I can be generic enough for the acid I don't screw it up. I think it's acid. What does that make? I know you two know because you guys were looking at it.
Oh, the nitrogen triple bond thing structure?
Yeah, this was the HONO. Whoa, that's not supposed to be a W. And then I think phosphoric acid, but I don't remember that one. That's in the Sandmeyer. Which of those two options do you think is the better one? Probably the first one because less steps, yeah. Right. But that doesn't mean the second one doesn't work. It just means the first one's nicer. Okay, kind of makes sense? So realize there are other ways to go through and solve. If you see a multiple choice question that just lists 4 different syntheses and they ask which of these work, if you find one, that's the answer. Okay? But if they list 2 and then say all the above, then you're kind of dead in the water. You need to check everything. Okay? So watch out for that. Yeah, blocking group. That is another synthesis example. Yeah, we'll do it. We'll think about it. Let's look at it. I want to make this guy, but I want to make it from benzene. So, how do I get bromine? Where would it direct? What's that?
Like from the starting maybe?
So, okay. It's not obvious on the question on why yet, so let's not worry about that. How would I get this piece? That's our acyl chloride with the aluminum. Oh, I think I made this. I may have made a mess out of this one. Whoops. How do we do the top one? Okay. So it's now just a question of doing those. But what order do you do them in? All of them are deactivators, meaning what? They would all direct to the meta position. So that's going to be problematic. Right? So, ideas. Yeah, this I just noticed a massive issue with this one. So we'll just work with the best we got. Okay. So if we put on the Fe, the bromine first. Oh, I should turn it on its side. They'd be para and ortho to the bromine. Is that okay? Halogen. What's special about the halogen? It does direct para ortho. Okay, well, where are those two things? Para and ortho. Okay, so what could we do? Okay, I heard add the acyl chloride. And then I also heard add the sulfuric first. Which one do we want to do first? Why the acyl chloride first? Okay. If I don't do the acyl chloride first, I'm just going to write AlCl3. What happens? Well, when I did the nitro, what would happen? The nitro would go to the para position, and I don't want it there. So I want to put that on first. Make sense? Okay. Another issue. If I put the nitro on first, let's just say magically, poof, it went to the ortho position, even though it would probably go to the para. So let's, poof, there it is, ortho position. What's now the problem with the ring? It's super deactivating. That's going to make the Friedel-Crafts acylation a little bit more difficult or challenging. That's the part that I misinterpreted just now in my brain. Okay? The Friedel-Crafts acylation should still work because it's an acylation. It'll just be harder to get to function. But it makes sense to do the acylation first because we'll maximize the yield and it blocks the para position so the nitro goes where we want it to. Okay? If we switch the order of these, we'll either one, drop yield or not make the right product. Does that make sense? This is kind of like a favorite way to ask synthesis questions on the ACS, because it's now just stringing together what directs where. It's just piecing those puzzle pieces together, okay? With a relatively minimal strain on reagents. Make sense? Questions on that? Okay. So, reduction of the aromatic. We did the triple bond earlier and we had the trans. We can do the same thing to aromatic rings. Turns out sodium metal and ammonia, not a particularly nice solution, and that will reduce aromatic structures. Okay? So really, really nasty. To do that, it has to split the double bonds. Okay? They need to go to opposite sides of the structure, because if they start to be conjugated, then it's like, well, all I got to do is ditch a hydrogen and I'm now conjugated again. Okay? So that in and of itself isn't a big deal. What becomes a big deal is what happens, yeah, ignore all that, when I do a substitution. Okay? Because if I do that substitution now, there are now two possible products. I could have that, or, oof, or that. You can at least tell the difference, right? All right, well, so which one do I get? Why would I get the second one? Touche, fair answer. So try again. Why would you get the second one and not the first one? And you're wrong. Yeah, I think so. Never mind, you're right. So the mechanism is drawn up there for a reason. And notice that's not the full mechanism. That's kind of a lie. It's mostly the full mechanism. What is the most reactive thing you see? So the radical is there, yeah, radical or charge. Right? How many of you like radicals? Okay, so let's ignore the radical and let's focus on the charge. Okay? Let's focus on that negative charge. Okay? Or that negative charge. Okay? To be more stable, that negative charge needs to be what? Neutralized by putting it near what? More electrons or less electrons? Less electrons, right? So let's go through and take a look at the products that we drew. That blue carbon was the one that was negative through the intermediate. Same deal here. Okay? Either of those blue carbons picked up a negative charge in the course of the reaction. The only one that's going to be super relevant to us is this first structure. Why is that first structure going to be so important to us and not so much the second?
The negative on the tertiary carbon.
I put a negative on that tertiary carbon. It's not even the blue position that's important. It's now the purple one. That purple one is the most distinctly different. I'm putting a negative charge on a tertiary position. Is that good or bad? That is incredibly bad. Which structure is favored? The one on the right. Okay, so cool. We can just apply that logic to everything else. So we go down. Let's repeat our drawing. Make sure I draw this all out right. So if we drew this, there's the first structure, which we just said would be horrible, and here's the second structure. Right? And that means the second structure should be the one we get again. Why not?
Because we have resonance in that.
Okay. What is different between that first group or that first reaction and the second reaction?
Carbon, oxygen can do resonance.
The identity of atom X connected to the ring. In the top case, that atom X has more electrons than hydrogen, which would mean I don't want to put the negative charge right next to it. The bottom structure, atom X, has less electrons than hydrogen. That means put the negative charge as damn close to that as possible. That's going to be the first structure. And I end up not seeing the second. So we still have to evaluate what that atom is that's connected to the ring. It's going to dictate how the chemistry occurs. Kind of makes sense? So similar in concept to what you're doing with the EAS. This is again one that's kind of a strict memorization thing. If you can remember the negative charge, that's where I would focus, because then I could just apply that out to my resonance structures. Okay? Good? Okay. So that's the part of the slide that you cheated and looked at. That's okay. Aromatic rings reacting oddly. So let's take a look. First reaction, top one. Why does that look odd to you? So I was missing out at home, you know, with gesturing, because I gestured a lot right there. I'm talking about the top reaction. That would be the one in the blue box. Why does that look weird? Right. I'm taking a nucleophile, and I'm reacting that with an aromatic ring. And aromatic rings act as wait, what? Can a nucleophile react with a nucleophile? That doesn't really make any sense. That means somehow or another the aromatic ring must be acting as an electrophile. Well, that goes counter to all chemistry we've already studied. Okay, that doesn't make any sense. The aromatic ring should act as a nucleophile. So that, in and of itself, is weird. Okay, why might the ring act as an electrophile in that case? The bromine's a deactivator, the nitro's a deactivator. Both of those being deactivating groups help to allow the ring to act as an electrophile. What else is special about the bromine? It's a good leaving group. Right? So that bromine can start to leave at the same time as our nucleophile comes in and attacks. Is this an easy reaction to run? No, that's why it's running at 70 degrees Celsius. Okay? Which isn't super hot, but that would be an uncomfortable bath. Okay? I think that would be. Okay. I don't know Celsius. So we end up getting a weird substitution there. This is not a super clean, as I'm showing here, SN2 reaction, because the backside of that carbon-bromine bond is the aromatic ring. So we can't do a backside attack. We can't have the leaving group leave on its own, because then, well, that would be forming a carbocation, that would be SN1, and that's not a stable structure either. So what ends up happening is this weird cross-hybrid substitution reaction known as an SNAR. Substitution, nucleophilic, AR. Oh, aromatic. It is a nucleophilic aromatic substitution reaction. It's its own mechanism. It generates its own unique intermediates that happen to follow this. I would bet that nobody thought this would work, and I'm surprised it's not named. Okay? Because we've got evidence to show that EAS makes sense. Why on earth would this happen? Someone probably went through adding the base, assuming something else was going to happen, and then something weird happened to their aromatic ring. We're like, what the hell? And I had to backtrack to figure out what happened. Okay? The next one. Let's move to the bottom one. What's weird about the bottom one? What? We get two different products. That's weird. What else is weird?
NH2, which is a nucleophile.
NH2 is a nucleophile. Again, we're having the aromatic ring act as an electrophile in the presence of the NH2. Okay? Also very, very odd. Okay? So we're getting two products, and again, the ring is acting as an electrophile. Okay? In the first case, it was okay to say the ring acted as an electrophile. Why? Deactivators. Why is that not so nice for the bottom one? It has an activator. So something weird is going on here. Okay, well, what else changes as we go from top to bottom? Yes, NH2 is a base. What can you tell me about that base in comparison to sodium hydroxide?
Stronger.
NH2 is a stronger base. Why might we need a stronger base? The ring isn't as deactivated. We need a stronger nucleophile to initiate this reaction. Okay? That still doesn't explain the two products, okay, per se. We did say it acts as a base. Bases typically favor elimination reactions. You were fishing for something else, right? No. Favor elimination reactions, which would mean a double bond. What is special about a double bond? All double bonds require two atoms, which means there'd be two sites of reactivity. You mean there's two places that could react with the nitrogen? Yes. Okay. So maybe what's happening in this bottom one is a legit elimination. And you might be saying, well, isn't that really weird to be doing an elimination on an aromatic ring? Right? Isn't that what you should be saying? Yeah, why is that weird? Since you didn't ask the question, I now get to ask you. Why is that weird to do that elimination? There's already a pi bond. So if I'm saying to do an elimination, what I'm saying is happening is I have to have another pi bond. Right? That's an elimination reaction. Why is that weird? Can I have another pi bond? Why is that weird? That's going to be really hard to have that ring fold up on itself to be able to get the triple bond there. In fact, I would think that's impossible, and I would be wrong. Turns out that that structure can fold up on itself and form a triple bond. It's a highly strained structure, which is why it's insanely reactive, but we do know it exists. Right? So, within these systems, what we're talking about first is an NAS reaction. Number one, we have to have an electron poor structure because the ring is acting as an electrophile. The ring, by definition, must be electron poor then. Okay? We have to have a good leaving group. This is where our halogens come into play. This is where we have bromine, chlorine, iodine. Okay? And the leaving group must be positioned ortho or para to the withdrawing group. Why? Well, yes, it's saying we must investigate the mechanism because what? What do you think we're probably going to find?
Who's the positive charge on
It's going to start to show how the electron density shifts so that we can stabilize our intermediates better if we have the electron withdrawing group ortho or para. Okay? Do I have a pretty mechanism? Because I don't want to draw it out. Damn it. I still don't want to draw it out. And I still probably will. So we'll see what happens. Okay? So the reasoning we have to have that alignment is because of the electron withdrawing. Oh, son of a watch it. Monkey. I just feel like I got to show it. The nitro is electron withdrawing, which means this electron density gets pulled out, right? Which would be putting a positive charge here, right? Okay, who cares? But then I could show resonance where that pi bond moves down there, which would then mean the positive charge would show up where? Whoa, that was weird. I'd put my positive charge there. What is special about putting the positive charge there? That's where I want the nucleophile to attack. That's pretty useful. What about in the other one? Well, the nitro draws out. I would put the positive charge there. Not relevant. Okay. Or I check the other resonance. Put the positive charge there. It's not where I want the nucleophile to attack, so let's do another resonance. I would put the positive charge over here. Is the positive charge ever located at the position where the leaving group needs to be? No. What does that mean? No reaction. And that reaction just doesn't initiate, whereas the other one will. Okay? So if we look at the resonance officially through the intermediates, we have to be looking at all that, but I don't feel like drawing all those out. Okay? We can see that we build the positive charge where it needs to be if we're orthoparent. If we're meta-substituted, it doesn't work. Okay? So, things that we've gone through and done. Chlorine with sodium hydroxide and heat. We don't get a reaction. Why might we not get a reaction for the lower left? What's the problem with that blue box reaction? Why would it not occur? Shall I flip back a couple slides? Nope. Rule number 1. Must be electron poor. To be electron poor, what do we need? A strong electron withdrawing group. What's the problem with, I knew you were going to do that. What's the problem with this structure or that reaction? There's no electron withdrawing group. There's no strong electron withdrawing group. That's why it doesn't work. Okay? Somebody got a little bit creative and said, well, what happens if we change the temperature? Just a little bit, right? 70 degrees to 350 degrees. Okay? Potato, potato. Yeah. That's like, you know, a slight bubbling of my skin to now I'm dissolved. And they noticed, whoa, what the hell? It actually occurred now. Okay? They've given it enough energy to clear whatever activation barriers are there, and it actually worked. Okay? So, well, somebody else said, well, that's kind of neat. You could do that by giving it enough energy. You could also go through and say, I don't know, use a little bit less heat and instead use a stronger nucleophile, like sodium amide. Okay? And sure enough, they went through and tested that, and yeah, cool, that worked. The stronger nucleophile was able to overcome the issue of the ring not being as fully deactivated, and we could still run that substitution. Okay? This is where things then went sideways, because someone started playing around with this and noticed that on substituted structures, what the F, you got 2 products. Why did we not see 2 products with the bottom one? There's only one substituent. I wouldn't be able to tell how many products came out of that because both the products would be identical. The instant I added another substituent to it, now I can see it, and now something becomes all sorts of god-awful weird. Why the hell can I get 2 products? If I was following the NAS mechanism, it should have just done the substitution where the leaving group was located. But that's not what happened. Okay? So someone had to dig around in this a little bit, and they noted, let's see, do I give the answer away right away? Ignore all that. They noted, come on, yeah, ignore all that, that if they ran this reaction and did it in the presence of furan, they got that weird product out of it. Like, wait, what? That would be a Diels-Alder product. The only reason a Diels-Alder product would have happened is if there was an active pi bond. But the aromatic ring doesn't have active pi bonds for Diels-Alder. Those are neutral. So that must mean somehow or another I'm making an active pi bond on an aromatic ring. That must mean I'm going through this weird triple bond structure. Okay? So we actually have experimental evidence for the benzyne intermediate. Okay? And they could go through and test this with radio labeling. This is pretty much just saying what's up at the top. Okay? Sodium amide, yes, is a really good nucleophile. It is also a really good base. And so what ends up happening is that that really good base comes in, removes a hydrogen, and forms the anion on the ring. That anion can come in to form a pi bond to kick out the chloride. That gets you the benzyne intermediate. Okay? The ACS loves this, and I don't blame them. You have a triple bond in an aromatic ring. That's just all sorts of bizarre and weird and cool. So yes, they love looking at this intermediate. Okay, so it is an important one to evaluate. What is the hybridization of that starred carbon? It is sp. Okay? It is a full 180 degrees. And yes, this structure doesn't seem to make much sense, but we know it to exist. because of the evidence that we found, primarily the Diels-Alder. Okay? And really the argument coming out of this is that we aren't forming a formal triple bond there, that really what we're forming is the structure shown on the right. Okay? And you might look at that and say, well, what is that? That is a diradical. Instead of forming a formal pi bond there, we actually have two radicals that are sort of interacting with each other in the way that we would expect a pi bond to interact. But it's actually a diradical. That diradical can then go through and react at both of those positions with the sodium amide. Okay? Because that structure now doesn't really want to be negative, or for that matter positive, the amide can come in and do a nucleophilic addition to an alkene-esque pi bond, okay, which is all sorts of extra weird too. But because there's now two positions on that alkyne that can potentially react, we get two potential substitutions, or apparent substitutions. That's where this reaction comes into play. Okay? So, our direct evidence comes from Diels-Alder. They said, this mechanism makes absolutely no sense. I don't believe you. They said, well, if the pi bond isn't there, then Diels-Alder won't work. And so they threw it together and Diels-Alder worked. They said, well, I don't care if you don't believe me. The science says I'm right. Okay? Same thing goes if you look at your standard kind of addition reactions, HBr, Br2, all of those. It undergoes the same types of chemical reactions that you would expect with a standard alkene. So we do have direct experimental evidence of the benzyne intermediate, okay? Which gets us maybe to the last slide, which is now our big review slide that has all of the content, okay? This slide should be out when doing the homework, okay? Because this has virtually everything on it. It doesn't have any of the Sandmeyer. I kind of apologize for that, but it's got enough crap on it already, okay? Make sense? And I was right. That never happens. More than once. Right? And, look at that, almost right.